Hello everyone, and welcome back to the channel. Today, we are solving Codeforces round 1018, Problem C, named Wonderful City. In this problem, we're given a grid of numbers, and our goal is to transform it into a state where no number is equal to any of its neighbors. That includes the cells directly above, below, to the left, and to the right. To make changes, we are allowed to increase all the numbers in a specific row or column, and each such operation comes with a cost. The task is to figure out the minimum total cost required to achieve the perfect state where all adjacent cells differ. Now, if this were a one-dimensional problem, say just a single row, it would resemble a basic dynamic programming task. In that case, we could define a state as solve of index and operation, where index is the current position in the array. Operation is a Boolean indicating whether we performed an operation at the previous index. From that state, we decide whether to increase the current number or not, a standard pick or not pick situation. Using memoization or tabulation, we can compute the minimum cost for the array. But the twist here is that we are working with a two-dimensional grid. So we need to extend this logic to rows and columns. The good news is, the same concept can still be applied. We divide the problem into two subparts. 1. First, we only care about vertical adjacency. That is, making sure grid at I, j is not equal to grid at I minus 1, j. Second, we handle horizontal adjacency, making sure grid at I, j is not equal to grid at I, j minus 1. Essentially, we treat the grid as rows and columns independently, apply the same DP approach to each, and calculate the minimum cost in each case. Finally, we add both costs, and that gives us our total answer. Now, a very important point. Why can we treat these two subproblems separately? Won't performing operations on rows affect the outcome when we work on columns? Let's prove it with an example. Suppose we have this grid, A, B, C, D, E, F. Let's first perform an operation on the last row. We increment all elements, A, B, C, D plus 1, E plus 1, F plus 1. Now we know B is not equal to E plus 1. Next, we perform an operation on the middle column, increasing the second column values. A, B plus 1, C, D plus 1, E plus 2, F plus 1. Now, since B was not equal to E plus 1, it follows that B plus 1 is not equal to E plus 2. So the condition still holds. This simple example shows that operations on rows and columns can be handled independently, and we don't need to worry about them interfering. And that's the main insight that helps us break down the wonderful city problem and solve it efficiently. You can find the source code in the pinned comment below. If you found this helpful, please like, share, and subscribe to support my journey. It really helps the channel grow, and I truly appreciate it. Thanks for watching, and I'll see you in the next one.